So really quickly, a review of what we've done so far. We're starting probability, and we said probability is defined as the number of successful events divided by the total number of events. We gave you some vocabulary. We talked about a trial. That's an operation that you can't predict with certainty. We had 3 trials already today as people came in late and we rolled the dice. I didn't know what we would get. I did know it would be between 1 and 6 inclusive. I knew it would be a whole number. You can't roll a die and get 3.4 as an answer. So there are certain restrictions. In fact, that's the sample space. I know that when you roll a die, the sample space is 1, 2, 3, 4, 5, or 6. An experiment consists of 1 or more trials. An event is a subset, so we had the event 1, we had another event 1, and then, Charmaine, we had the event 4. Those were the rolls that we've had on our die. We also talked about odds. So what's the probability of rolling a 6, 1 out of 6? What are the odds? 1 to 5, because there's one way of rolling a 6, and there's 5 ways of not rolling a 6. The odds are 1:5. The probability is 1 out of 6. And that's going to be a little tricky. Make sure you read the question carefully. Are they asking for the probability as a fraction or decimal, or are they asking for the odds? I tend to emphasize the probability more. I'm going to cover odds. I'll ask you a couple of odds questions on your test at the beginning, and then I'll probably say, I'm more interested in what's the probability. And in fact, I have to catch myself. Often you'll hear me say, hey, what are the odds? And what I really mean is, what is the probability? Because in the old Math 12 course, we didn't distinguish between the two. We talked about complementary events. The complement of rolling a 1 is not rolling a 1. And we can show that by 1 with a bar over it. Our symbol for not was a bar over it. And if rolling a 1 is 1 out of 6, the complement will be 5 out of 6. We said that the probability of something guaranteed, Emma, is 1, 100% 1. Probability that something can't happen is 0. Everything else is somewhere in between there. As a very handy-dandy shortcut, this idea of the complement, you know that the odds of something happening plus something not happening must be 1. In other words, something happens or it doesn't. But we said, often, Brandon, it's going to be easier, even though they say find the probability of something happening, it's going to be easier to find the odds of it not happening and go 1 minus that. And you'll come up to 1, I think, later on today, if not in a couple classes. So we left off right here. And I finished by saying, you know what? If you can count it, you can almost, on your fingers, you can find the probability. But we're going to very quickly, Sean, get beyond the counting, the ability to count. So, you may recall, Christina, in the last unit on combinatorics, I tried to give you some tools. We started out drawing a blank, drawing blanks. And similar to drawing blanks was we kind of attached to it the notion of a Scrabble bag, imagining reaching in and pulling stuff out. We said for chooses, we gave you the bucket approach. Probably the single best tool I'm going to give you in probabilities is a tree. In fact, my fallback, just the way in the last unit my fallback when I was confused was to draw a blank and go to the fundamental counting principle, my fallback for probability is when in doubt, I go back to what's called a probability tree. Probability tree. So I have here calculating probabilities using a tree diagram with equally likely branches. And here's the question. What's the probability that in a family of 3 children, there are exactly 2 girls? Before we actually answer this, one of the things I love about probability, Kyla, is basic questions we all have a good understanding for. Kyla, what's the probability of rolling a 5 on this die? We all understand 1 out of 6. I've never had to teach a kid that. But as soon as you go even remotely tougher than that, our innate understanding is so bad. This is why we're all superstitious. This is why we all look at coincidences and think, oh, that can't happen. This is why we have such a bad understanding, why we're willing to try and find, oh, if you're a sports player, this is why sports players are so superstitious. We have such a bad understanding. Here's what I mean. So here's the question. What's the probability that in a family of 3 children, there are exactly 2 girls? Here's what I would like you to do. Off in the margin to the left right here, write down what you think the probability is as a fraction. Take a guess. What's the probability that if there's 3 kids in a family, exactly 2 of them are girls? Take a guess. Do this, because I want you to realize how bad we are at assessing probabilities. And by the way, this isn't that tough a question. It's only 3 kids. I can count that. How bad we are at actually coming to a conclusion on this. Y'all written down your guess? I'm serious. Write down a guess. Okay? With where we are now, Foster? You actually going to write down a guess after I said it the 4th time? Hey, excellent. Okay. Sean, can you read to me the little bold font title here? What did I say?
Calculating probabilities using
tree diagrams. Here we go. One of the best things I can show you, a tree diagram. And here's what I mean. How many kids?
3.
So I'm going to draw a 3-level tree. Why? How many kids?
3.
So I'm going to say this. First, I'm going to turn the pen on. For the first level, the first child could be a boy or a girl. I'll call that boy 1, girl 1. And I'm going to assume that the odds of a boy or girl are 50-50. They're apparently actually not quite 50-50, but close enough. There's a slightly greater chance of having a girl, which is why there's slightly more females on the earth than there are males, but close enough. Then let's represent the second child. Boy 2, girl 2, boy 2, girl 2. The third child, boy 3, girl 3, boy 3, girl 3, boy 3, girl 3, boy 3, girl 3. So I wrote down here solution steps. Draw a tree diagram to represent the possible arrangement of boys and girls in a family of 3 children. Done. Each branch is equally likely. Why? Assumptions. We are assuming the odds of having a boy and a girl are 50-50. 1 and 1. Determine the number of branches that contain 2 girls. So looking, how many of these branches contain exactly 2 girls, no more, no less? Well, I think that one there, yes? Follow it down. I think this one here, and I think this one here. Follow it down. Just give me a second, I got a latecomer. And so here's what I mean. If you start at the very top, and I go, this one here is boy, girl, girl. This one here is girl, boy, girl. This one here is girl, girl, boy. Those are the only 3 branches that contain exactly 2 girls. Why not this one? Oh, how many girls does this far right-hand branch actually contain? 3. And the question said exactly 2. So, how many branches have a check mark? Probability of 2 girls, 3 out of how many branches grand total? Count across. Yes, 8. Did anybody actually guess 3 out of 8? I've never had a single student ever guess that. Because most of the time, when they think 3 kids, 2 girls, they're trying to do, the number 8 never pops into their head with 3 children and 2 girls. It's an unlikely denominator. Oh, and even the number 3 as the total number of possibilities doesn't ever pop into their head because, well, 2 girls, I was, huh? But when you draw a tree, it becomes pretty obvious. It becomes pretty obvious. Okay? Example, research shows that the probability of an expectant mother selected at random having twins is 1 out of 32. That's the probability. What are the odds in favor of the expectant mother? Okay, underline the word odds. Odds are written with the little colon. Okay? The odds are not 1 out of 32. The odds are in favor 1 out of, not out of, 1, 2, 31. Because there's 31 ways you can't have twins. There's one way you can have twins in that fraction, 1 out of 32. That's the difference between odds and probability. Oh, what are the odds against an expectant mother having twins? 31 to 1. But again, the key word here, Rachel, is odds versus probability. Probability, 1 out of 31. Probability of not having twins, 1 out of 32. Probability of not having twins, 31 out of 32. That would be the complement. Odds, how many successes, how many failures, with a colon in between them. Example 3. A computer randomly selects a university student's name from the university database to award a $100 gift certificate for the bookstore. Okay. The odds against the selected student being male are 57 to 43. Determine the probability that the randomly selected student will be male. Okay, our symbol that we're using for probability is a capital P. What would a good abbreviation be for the word male? Okay, probability of capital M is, if the odds are against being male 57 to 43, what's the probability of being male? Yep. Close. 43, not out of 57. No. No. Because there's 100 total different people, right? 100. The same way as we went here, what we were saying is, oh, if there's a 32, you're saying there's 32 different possible outcomes. 1 success, 31 failures, or 31 successes, 1 failure. Oh, when you're saying this, you're saying if the odds are against 57 in favor of the ladies, 43 in favor of the guys, what you're also saying is there's a total number of 100 outcomes, a total of 100 possible outcomes. See the subtle difference? It's a little confusing, but when you wrap your brain around it, and again, I think I said Las Vegas almost always, gambling, they almost always give the odds. Why? Because usually the odds numbers aren't as remote seeming, and so it's more likely someone will gamble. Next page. Example 4. So we have this, let's imagine we have a little spinner. You know, one of those little games that you spin. And we're going to imagine that you can't possibly stop on a line. We're always going to stop in an area. And speaking of stop, example 4, it says when the pointer is spun how many times? Twice. You know what? 2 spins, I'm going to do a tree. On the first spin, what could I get? A 0, a 5, a 10, or a 20. So my tree is going to look like this. On the first spin, I could get a 0, a 5, a 10, or a 20. There's spin 1. On the second spin, what could I get? A 0, a 5, a 10. So it's going to go like this. 0, 5, 10, 20. The only problem with trees is they get, you know what, I need to make mine a little wider to make this fit for you guys. You kind of got to spread out. 0, 5, 10, 20, 0, 5, 10, 20, 0, 5, 10, 20, 0, 5, 10, 20. How many outcomes are there? If you can count it, you can solve it. How many outcomes are there? How many outcomes are there? Yeah, sorry, how many? Okay, so it's going to be, first of all, probability of $10. It's going to be out of 16. How many different ways can you win $10? Let's see. I'm going to put a check mark underneath each one. Here, yes? Oh, here, because you could win $5, $5. That's $10. Here, you could get a 10 and a 0. I think that's it, yes? So what's the probability that you win a total of $10? 3 out of? Okay. What are the odds that you win $10? 3 to, not 16, 3 to 13. 3 ways to win, 13 ways to lose. See the difference, Justin? C, find the probability that the same number comes up on each spin. I'll change colors. I used red last time. I'm going to use green. Same number. You know what? I can probably just count, so I'm going to go like this. Probability of same number. How many ways can the same number come up? Sorry? 4. Oh, yeah, because there's a 0, 0, right? You can get a 0, 0, you can get a 5, 5, you can get a 10, 10, you can get a 20, 20. Yes? This is more than a little annoying now. So, how many ways were there to get the same number? Out of 16. Now, I know in lowest terms that's 1 out of 4. I will only reduce at the very end if I need to. Again, I said last day, I kind of find that 4 out of 16 more informative because it tells me how many ways were there to get a success? 4. How many possible outcomes were there? 16. D, what are the odds that the same number doesn't come up on each spin? What to what? I'll give you a hint. 12 to. Now, this is almost always written in lowest terms. So what would 12 to 4 be in lowest terms? 3, 2, 1. Mr. Dueck, how did you do that? I reduced the fractions, and please remember, I did show you if you're clever. It turns out you can reduce fractions, even though this isn't a fraction. I treated it like one to reduce it. You can reduce fractions on your graphing calculator. 12 fraction button 4 is 3 to 1. You have to clue in there's a 1 there, I guess. Example 5. When 2 bills are randomly selected from that pot without replacement. Ooh, let's underline the phrase without replacement. Find the probability that you win a total of $10. How many bills are we selecting? 2. This is going to be a 2-level tree. A 2-level tree. When I first reach in, what are my possibilities? What can I get? So on the first draw, there's going to be a 0, a 5, a 10, or a 20. What about on the second draw? It depends because we're not replacing. I think my second level of branches, each little mini level is going to look different from the one next to it. Because I think if I pulled a 0 out, I have a 5 or a 10 or a 15 left. 20 left, sorry. Thank you, Jordan. Here, I have a 0, a 10, or a 20. Here, I have a 0, a 5, or a 20. Here, I have a 0, a 5, or a 10. Yeah? If you do a good tree, then I argue, Brandon, the question kind of falls apart because the probability that we win exactly $10, first of all, what's it going to be out of? What's it going to be out of? 12. And where do I win exactly $10? Here. Here. I think that's it. Just those two branches. Yes, if I walk down the branches? 2 out of 12. If I had said the odds, that would be 2 to 10, or the odds are 1 to 5 against you. Sorry, 1 to 5 in favor of you winning exactly $10. Is that all right? Turn the page. A couple more on odds and we're done. A hockey game has ended in a tie, so the winner will be decided by a shootout. The coach must decide whether Ellen or Brittany should go first in the shootout. She'd prefer to use, or he would prefer to use her best score. She would prefer to use her best scorer first. So she's going to base her decision on the players' shootout records. Ellen has scored 8 goals in 13 attempts. Brittany has scored 10 goals in 17 attempts. Who should go first? So this is where you can start to apply probability. Those of you that are getting into sports, you may have noticed in the past 10 years in baseball and in basketball and in hockey now, this idea of what they nicknamed sabermetrics, this idea of applying statistics everywhere to try and get to the heart of true stats as opposed to just how many points did you score. Were they meaningful? Even hockey for years has had that plus-minus stat, which really isn't that good. There are better stats than that. We try and use these as a guide to make the best decisions in sports, heck, in life for that matter. Who should go first? How could you figure this out? Ellen, should Ellen go first? Well, you know what? Let's write these as probabilities. So I think we have this. Probability of Ellen scoring is 8 out of 13. Probability, can't even say that, of Brittany scoring 10 out of 17. You guys kind of suck at fractions. If I ask you what's bigger, 8 out of 13 or 10 out of 17, because they're both prime numbers on the bottom, that's a tricky one. Hey, change them to decimals. Get your calculators out, change them to decimals. What's 8 out of 13 approximately equal to as a decimal? Sorry, loud? 0.62. What's 10 out of 17 equal to approximately as a decimal? 0.59. Who's more likely to score? She's smiling. I saw her suddenly. Me! Who's any baseball players here? Like if you watch the major leagues, for example, they have the stats left, right, and center. I mean, anytime a pitcher comes in, they'll tell you what his statistics are versus that particular batter on a sunny day with the wind blowing across the field in this particular stadium. I mean, they really try and get it down to a science. Again, does that guarantee that you've made the right decision? No, because nothing prevents me from flipping 10 heads in a row on a coin. It's possible. But Over the long haul, if you generally go with the odds, you will find over the long haul, you'll have more successful outcomes than not. A group of grade 12 students are holding a charity carnival to support a local animal shelter. The students have created a dice game that they call BIM and a card game that they call Zap. The odds against winning BIM are 5-2, it's against, and the odds against winning Zap are 7-3. Which game should Madison play? Let's look at the odds of winning, because if this is against winning, I'd like to know the odds of winning. That's what's going to tell me what to play. So what's the probability of winning BIM? Can you see how you get it from the odds there? 2 out of 7. What's the probability of winning Zap? 3 out of 10, yes? Okay. Both of those, I can tell just by looking at them, are less than 50-50. Both of these, I can tell the odds are not in my favor. So in real life, I'd be expecting to lose. Okay, if I was doing this at a charity, if you guys were running some kind of a carnival and you had games of chance and I was paying for them, I would look at this and I would say, you know what, I'm making a $20 donation. However, I'd like to at least increase the chances that I'm not making a donation, that I might come out ahead. Which game would I play? Which game would you play? How could you figure it out? Oh, make them decimals? Okay. So 2 out of 7 is approximately what? 0.29? 3 out of 10, hey, that I know. 0.3? Which game would I play? Barely. In fact, you know what? Those are close enough that if BIM was funner, I'd probably swallow that 1%, that 0.01 decimal, and I'd say, I'm going to play the funner game, even though technically the odds of winning the other game are slightly more in my favor. Oh, I'm going to have more fun here. Any questions there? So what's your homework? From your textbook, page 310 to 312, numbers 1 to 7, 9, 11, and 14. Some of them are tricky.